Okay, let's look at an example of changing variables in a double integral. This is an example from the textbook, but we want to go through the details and also illustrate how we can solve similar problems. First, we need to identify the equations that we want to use, the new variables. And if we look at the double integral over here, we already tried that this integral over here, e to the power x plus y over x minus y, is difficult to integrate. So here is the motivation. Here is the motivation, difficult to integrate e to the x plus y and x minus y. But relatively easy if we have e to the, say, s over t, this kind. So this gives us the motivation. So this is what we're going to do. Suggest we have a change of variable that's x plus y is equal to s and x minus y is equal to t. Of course, there is no guarantee it can work because it depends also on the domain. For these problems, the domain and also the integrand are specially designed so we can actually solve them easily after making a transformation. So we need to have a transformation so that x is equal to something and y is equal to something. That way we have something about s and t, and y is equal to something about s and t. And that way we can do the substitution. And how to do that? We call these two equations, equation 1 and equation 2. So if we add these two equations, then we have, this is just elimination method, by the way. We have 2x is equal to s plus t, and x is equal to 1/2 of s plus t. Okay. And similarly, if we use 1 subtract 2, then we have 2y is equal to s minus t, and then we have y is equal to 1/2 s minus t. Okay, so now we have the transformation. So we have transformation x is equal to 1/2 s plus t, and y is equal to 1/2 s minus t. And remember, we need to transform all three objects involved. Number one, we need to transform the domain from domain D to domain D tilde. Domain D is described by x and y. So here we have the domain D over here. This is domain D. Okay? And then we need to change that one into D tilde. How do we do that? We will just replace x, y by s and t and figure out 4 new lines, or in general 4 new curves, and then we try to see what kind of domain we have. Okay. So let's first look at D, even though it's not necessary, but it always helps. So D, what we have over here is x is equal to 0, that's y-axis. This is x equal to 0. And then y is equal to 0 is x-axis. And then x minus 1 is equal to 1. That would be this one over here, negative 1 and 1. When y is equal to 0, x is 1. When x is equal to 0, y is negative 1. And so this is what we have. This is 2, negative 2. And we do have a trapezoid. So this is what we have. This is our domain D. Okay. And then look at these 4 lines. We're going to transform them into 4 lines about s and t. X is equal to 0. That means 1/2 s plus t is equal to 0. And that means s plus t is equal to 0. How about y is equal to 0? That's 1/2 s minus t is equal to 0. and that means s minus t is equal to 0. And this method always works because we are transforming all the boundary into new coordinates. So that should actually work. And then x minus 1 is equal to 1. That means we can already see that because x minus y is t. So that means t is equal to 1. This is t equal to 1. And x minus y is equal to 2. That's t is equal to 2 because we know the change of variable is simply x minus y is equal to t, right? We have it over here, xy minus y is equal to t. All right, now we have these 4 lines, and we're going to re-sketch this d prime, d tilde over here. So that's going to be s plus t is equal to 0, s minus t is equal to 0, and t is equal to 1, and t is equal to 2. So we're going to try this one over here. Okay, we can use any. You can use horizontal t or s, doesn't really matter, but let's just say this is what we have. And s minus t equal to 0 means s is equal to t. So this is the one. Okay, s is equal to t. S plus t equal to 0. That's t equal to negative s. So that's what we have over here. Okay, and then t is equal to 1, and then t is equal to 2. So what do we have? We see over here is this new area, this trapezoid over here. Okay? And that's our d tilde. D tilde is this area. Okay. Now, after this change, look at the integrand. This is always the easiest part. E to the x plus y over x minus y. That one goes to, if we remember, that's e to the s over t. Okay, and that's what we have. Yeah, because x plus y is s, and x minus y is equal to t. Now, this is the second part. We need to do the transformation. This is the first part, the transformation. Third part, we now need to look at dx, dy. Remember the notation. We are saying this is going to be equal to partial x, y, and partial st, the absolute value of the Jacobian. And we will calculate the Jacobian separately over here. This is a determinant. Take the partial derivative. Remember, we have x is equal to 1/2 s plus t, and y is equal to 1/2 s minus t. So now we take the partial derivatives and find the determinant. Det means determinant. Take a derivative of x with respect to s. You have 1/2 of x with respect to t is 1/2 again. And then do the same thing for this second y function over here. And then we have again 1/2 and negative 1/2. Okay? And then we see the determinant is negative 1/4 minus 1/4, and that's going to be negative 1/2. So, so in order to find dx dy, we need to find this Jacobian. After we find the Jacobian, then we write down dx dy. So we now have dx dy is equal to, I need to erase this one because it's not really equal. This over here doesn't work. Now we have this negative 1/2. We have this Jacobian over here. We have just calculated. Okay, and that's going to be negative 1/2. So it's going to be 1/2. Now we are ready to put all these three things. So the integral over d, e to the x plus y, x minus y, dx dy is equal to the integral over d tilde about s and t, e to the s over t, and then we have over here times 1/2. And yeah, I again forgot this part is over here. I need to have ds dt over here. Otherwise, it's not going to work on ds dt. This is a change of, we say, the area element. and then we have ds dt. Okay. Now, look back at the domain we have, so we can see that it's easier to integrate s first and then t second. So we draw a strip over here. So that's over here, right? This is the one. For each fixed t, and then s goes from this point and to this point. And we can illustrate this one over here. Okay, so what it means is that the domain D we have over here is the following. For each t between 2 and 1, s is between negative t and positive t. Okay. The reason is this line over here, this is t is equal to s, or s is equal to t, and this one over here, s is equal to negative t, right? So that's the domain we have. So convert this one into an iterated integral, then we have from 1 to 2, that's for t, and then for s, we have negative t to positive t, and e to the s t, and then 1/2 over here. And then this is ds and dt. Let's finish this computation to see if it's possible to get the value. And then we have our 1/2 can go to the front and integrate e to the st. Now remember, we need to use the simple integration by substitution. This one over here is going to be equal to something like est, right? But you actually need to put t over here in order to have the right antiderivative. If you take the derivative with respect to s, you'll get e to the s over t, right? If you take the derivative, this is the right antiderivative. Take derivative with respect to s, this is something we have, t times 1 over t, e to the s over t. And that's e to the s over t. So that's the right integrand, right antiderivative we have. And then we have over here, we have t, e to the s over t. And then plug in t and negative t, and then dt. Okay, so you will see that this integrand over here now becomes relatively easy. S is equal to t, so it's t, and then it's e. And it's negative t, then we have e to the negative 1. Okay, and then dt. So e is a constant, so we can pull it out. This is e minus e to the negative 1 over 2. And then integrate from 1 to 2 and t dt, right? And then we have e minus e to the negative 1 over 2. And this is 1/2 t squared, and plug in 1 and 2. And then we are almost finished. The computation is a little bit long, but as long as we are patient and try to be accurate, and that's going to be okay. So this is going to be 3/4 and e to the negative 1. All right, that's the end of this computation. Let's try to recap of what we have done over here. So first, we recognize from over here that we need to make a change of variable called a transformation, right? And this is our idea over here. And because after we make this transformation, we expect to have a simple integrand. Otherwise, we cannot really get the value. So then we find our transformation by solving the equations over here to get two equations about x and y. And the lengthy part over here is the transformation of d. But we have an idea that each line over here is transformed into lines about s and t. So 1, 2, 3, and 4. And then we re-sketch the diagram of this new domain, the tilde. And then we transform the integrand, and then we calculate the Jacobian by looking at the partial derivatives over here. And then we change the dx dt part. Okay. And then when everything is ready, we put it into the old double integral to get a new one. And the new one, fortunately, is easy enough to actually integrate by converting it into an iterated integral. And then we get the final answer over here. Okay. All right. That's all.